So we want to study complex functions, a function which takes a complex number as an input and it spits out a complex number as an output. And following our Plan B philosophy, we want to understand, first of all, the algebraic picture. How do we understand, in this video, the relationship between a complex function and various functions of real variables? So what is the nature of that correspondence and how can it go in both directions? And then in our next video, we're going to take the step into the world of the transformational geometry. How can I understand a complex function as a transformation of the complex plane? This is going to help us to unlock our geometric perspectives that when we study real valued functions, we may have gotten just from the graph of a real valued function. But for complex functions, as we'll see, we have to work a little bit harder because complex functions geometry is a lot richer, and we can't just look at the graph of a complex function. It doesn't exist in a visualizable to our eyes and brains way in the way that a real valued function did. So first things first, though, let's take a look at some algebraic questions, and in particular, what is the relationship between a complex function and real valued functions, and how can that go in both directions? So the typical way that we make this correspondence is if you give me a complex function whose input is a complex number z, well, that complex number z has a real part and an imaginary part, which are real numbers, x plus iy. Right? And so if I stuff x plus iy into my complex function, it's going to do its complex function thing. It's going to spit out a complex output, and then that complex output is also going to have a real part and an imaginary part that we're going to call u and v. Right? So our definition is that if you give me a complex function, I can give you two real valued functions of two real input variables. We're going to call them u of x and y and v of x and y. And they have the property that u of x and y is the real part of the output of f when the input is x plus iy, and v of xy is the imaginary part of the output of the complex function f when its input is x plus iy. So this is, again, a way of hopefully letting us access our understanding of how real functions, in particular real valued functions, functions that spit out a real number as output, and in this case take an ordered pair of real numbers as input. So we study these functions quite a bit in multivariable calculus, and helping us to understand how a function operates in the horizontal and vertical directions of the complex plane. Right? So this is a really important avenue that will let us study functions like these. So what does this correspondence look like? If you give me a complex function, how can I determine the real and the imaginary parts of that complex function? So here's an example. Usually just replacing z by x plus iy is enough to be able to determine the real and imaginary parts. So this animation to my left, it's your right, shows how we might do this with the complex function f of z is 2z squared minus iz. So if I just replace z by x plus iy, usually I can just do the algebra that would be necessary to segregate the real parts and the imaginary parts. So squaring out, distributing, replacing the I squareds by negative ones, collecting all of the real terms together, all the terms that are not multiples of I, and the imaginary terms, those which are multiples of I, collecting those together, factoring out the I, and then the real portion becomes my real part u of x and y, the imaginary portion becomes v of x and y. And so that's how we can ultimately, in a lot of cases, determine the real and imaginary parts of a function, particularly for polynomial functions where just this algebraic simplification is enough to be able to segregate the real part and the imaginary part of the output of my function. And again, just like the real and imaginary parts of a complex number are themselves always real, the real and imaginary parts of a complex function are real valued functions. So we're never going to carry the I with us, right? We're just going to take the 4xy minus x that we got after we factored the I out of this term right here. So that's how we can determine the real and imaginary parts of a lot of different complex functions. There's going to be one example that we're going to work on in the investigation for this week that's going to take a little bit of extra work, and I kind of coach you through it. This is going to be one of the biggest things that's going to be challenging to do once we start looking at transcendental functions, non-algebraic functions next week, like the exponential function, for example. And this road actually runs both directions, kind of, right? That we've seen how to take a complex function and determine the two real functions, which are its real and imaginary parts. But can I also go the other way? If you give me a pair of real valued two variable functions, can I piece those together and make a complex function? Absolutely, right? You give me u of xy equals 1 plus x squared y, and v of xy is 2 minus xy squared. I can just take the 1 plus x squared y, make that the real part. I can take 2 minus xy squared, make that the imaginary part, piece those together, and what I get is a function that looks like f of x plus iy is 1 plus x squared y plus I times 2 minus xy squared, right? I can just piece them together. But the problem is I might not be able to take that complex function, and it is a complex function, it's a perfectly valid complex function, but it may be really hard for me to write it down using elementary algebraic operations on z equals x plus iy. Right? So one question that I would encourage you to ponder a little bit is, under what circumstances might we be able to put these pieces back together in a really nice way? And in what circumstances will that be fundamentally impossible? I want to do one more quick example that I'm just going to hand write out that kind of illustrates when this works well, but then you might imagine that there's a lot of cases in which it doesn't. So here's an example of when the miracle happens. You give us two real valued functions of two variables, and we can actually piece them together into a complex function that has a friendly expression in terms of z equals x plus iy. So if you give me u of xy as 2y squared minus 2x squared minus y, and v of xy is x minus 4y. Well, as it turns out, we can piece these together. So just by taking u of xy plus I times v of xy, in other words, taking u as the real part and v as the imaginary part of a complex function whose input is x plus iy, what ends up happening is 2y squared minus 2x squared plus y plus ix minus 4ixy. We can do some algebra, factor out a -2 from all of these first terms here, the y squared, the x squared, the xy, get those together. And it turns out that what we see in the parentheses here, the cofactor of -2, happens to be exactly x plus iy, the quantity squared. And ix minus y is the same as I times the quantity x plus iy. So we can rewrite everything in terms of x plus iy as a quantity. And because we can do that, we can then replace those x plus iys with z's and get a nice complex expression, f of z equals -2z squared plus iz. Right? So this, as you might suspect, especially as teachers yourselves, you probably notice that this example looks really contrived. And that's because it is. And so the question that gets us thinking is, well, how do we know when this is possible? Like when is it the case that if you give me two real valued functions, I can piece them together into a complex function that I can actually algebraically express in terms of z? And that's going to be a question that we're not really going to satisfactorily answer for at least a couple more weeks in our course yet. Because it turns out that in order to do calculus with complex functions, complex functions only have derivatives that make sense as complex functions themselves when there's a particular relationship between the real part and the imaginary part of those functions. You can kind of see this as analogous to the process in multivariable calculus, where if you give me a vector field in the plane, right, it has an x-coordinate field and a y-coordinate field, and those are real valued functions, that there needs to be a particular relationship between the x-coordinate and the y-coordinate functions of that vector field in order for that vector field to be the gradient of some potential function, right? So there's almost like a backwards process that we would need to do in order to know that these two separate functions kind of are inherited from a common ancestor in some way. So this, I guess the moral of the story is, this nice example is very contrived to be nice, and that this doesn't happen in the general case. There has to be something very particular about the functions u and v themselves and about their relationship one to another that allows us to do this piecing together into a friendly complex function. But the whole point of what we're doing here is forging that relationship between a complex function of a complex variable on the one hand and a pair of real valued functions on the other hand that are the real part and the imaginary part. That's the algebraic philosophy for how complex functions can be thought of as pairs of real valued functions. So in our next video, we want to make that algebraic idea geometric and visualizable. When we analyze real valued functions in the secondary curriculum, we have graphs. And a lot of that curriculum is about building relationships between algebraic properties of functions and graphical, visual properties of the graphs of those functions. What does that correspondence look like when we're dealing with complex functions? That's our next video.